Good morning, students. In today's class, I will explain two important CPU scheduling algorithms, also known as CPU scheduling policies. In our last class, we learned about different conditions under which CPU scheduling takes place. CPU scheduling takes place under four different conditions. The first one is when a process is moved from running state to waiting state. So this happens whenever a process needs to do some IO operation. The second condition is when a process is moved from running state to ready state. This happens whenever a high priority job arrives. The third one is when a process is moved from waiting state to ready state. This happens after the process which has previously requested for an IO operation has completed its IO operation. And the fourth condition is when a process terminates. If depending on these four conditions, CPU scheduling policies have been classified into two types: non-preemptive policy and preemptive policy. In case of non-preemptive policy, once the CPU has been allocated to a particular process, that process will give the CPU to the next waiting process only after that process is executed completely, or only if the process needs to do some IO operation. Otherwise, the CPU cannot be forcibly removed from the current process and given to the next waiting process. On the other hand, in case of preemptive, once the CPU is allocated to a particular process, before completion of the process also, if a high priority job arrives, then automatically CPU is given to that process, high priority job. And also, whenever after a particular specific time period is over, the CPU is removed from the currently running process and it is allocated to the next waiting process in the ready queue. We also learned about different criteria for selection of good CPU scheduling policy for any application. After attending, the main objective of today's class is to discuss about two CPU scheduling policies, namely FCFS or first come first serve policy, and the second one is SJF or shortage job first policy. After attending today's class, you will be able to understand the working of these two policies, and also you are learning about the merits and demerits of both FCFS and shortage job first. Let us start with the first policy called FCFS. It stands for first come first serve policy. It's one of the simplest CPU scheduling policy and it is very easy to implement. That means in order to implement a first come first serve policy, the programming is very simple program. Here, as the name indicates, generally, whenever the CPU is free, it is allocated to the process that has requested the CPU first. Or, in other words, the process which enters the ready queue first will get the CPU first. The process which enters the ready queue next will get the CPU next. And the process which enters the ready queue last will be the last one to get the CPU. So, the CPU allocation in case of FCFS is based on the time of arrival of the job into the ready queue. First come first serve policy is managed with the help of first in first out list or first in first out queue. Here, as the name indicates, when a process enters the ready queue, the process control block of that particular process is linked to tail of the queue because the new process is always added to the end of the queue or at the tail of the queue. At the same time, whenever the CPU is free during allocation, the CPU is allocated to the process at the head of the queue. The CPU allocation is from the head of the queue end, and the addition of the new process to the ready queue is at the tail of the queue. To understand how a FCFS algorithm works and how to calculate the different CPU scheduling criteria, let us consider a set of processes named as P1, P2, P3, P4, and their CPU burst time is 12 millisecond, 20 millisecond, 10 milliseconds, and 8 milliseconds. What do you mean by burst time? Burst time is the time required for the particular process to execute completely. How much CPU time is required for their process completion? We call it as burst time. So we'll show the working or we will show the performance of the first come first serve policy with the help of simple diagram called Gantt chart. Here, assume that all the four process P1, P2, P3, P4 are in the ready queue. That means they already entered the ready queue. Now the ready queue is full. Now assume that the CPU is free. Now what happens is the CPU should be given to these four processes. Which will get the CPU first? Because P1 has entered the queue first, means it will be given to the CPU. P1 will be given the CPU first. So now The time starts at 0 millisecond. Then P1 requirement is 12 millisecond mean. So for the next 12 millisecond, the CPU is allocated to P1. So P1 will hold the CPU for next 12 millisecond. So after 12 millisecond, it is given to P2. P2's requirement CPU P2 burst time is 20 millisecond. So it will keep the CPU with it for the next 12 millisecond. So it will get the CPU as 12 millisecond and it will hold the CPU with it for next 20 means 20 plus 10, it becomes 32 millisecond. Now P3 will get the CPU at 32 millisecond and it will keep the CPU with it for next 10 millisecond. So from 32 to 42 millisecond, your CPU is with P3 or CPU is processing P3. Now P4 will get the CPU at that clock 42 millisecond and the CPU is allocated P4 for the next 8 millisecond. So from 42 to 8 means 50 till 50th millisecond, the CPU is with P4. So this representation, we call it as a Gantt chart. Now, from the Gantt chart, we can calculate two CPU scheduling criteria. One is what is the average waiting time and what is the total turnaround time. Waiting time is nothing but the time the process has to wait in the ready queue to get the CPU. Let us start. From the diagram, we can observe that P1 will be given the CPU first. That means for P1, there is no waiting time because the waiting time for P1 is 0. P2, the waiting time is P2 has to wait till the completion of P1. So for P2, the waiting time is 12 milliseconds. P3 has to wait till the completion of both P1 and P2 means P3 will get the CPU at 32 milliseconds, 32nd millisecond. Similarly, P4 has to wait till the completion of all the three previous process P1, P2, P3 means it will has to wait for 42 milliseconds. So for P1, waiting time is 0. For P2, it is 12. You have to see this column. And for P3, it is 32. And for P4, it is 42. Waiting time, I mentioned P4, P1 0, P2 12, P3 32, and P4 42. Now you calculate average waiting time. How to calculate the average? Add those four numbers and divide it by the number of process that's equal to 4. So it becomes 86 by 4. It becomes 21.5 milliseconds. On a similar basis, we can calculate one more criteria called turnaround time. Turnaround time is time of submission to time of completion. How much time? What is the total time it will take from the submission time to completion time? We call it a turnaround time. Let us go back to the same Gantt chart. Now, all the four processes are in the ready queue. So your time starts at 0 o'clock. Your P1 execution is over at 12 milliseconds. P2 execution is over at 32 milliseconds. And P3 execution is over at 42nd millisecond. And P4 execution is over at 50th millisecond. So the turnaround time for P1 will be 12. For P2, it is 32. For P3, it is 42. And for P4, it is 50th millisecond. For P1, it is 12. P2 32, P4 42, and for P4 it is 50. So in order to calculate the waiting time, you look at this corner. For P1 0, P2 12, P3 32, and P4 42. To calculate the turnaround time, you see this corner. For P1 it is 12, for P2 32, for P3 42, and P4 it is 50. Now the total turnaround time is summation of all these four. It becomes 136 milliseconds. So from the Gantt chart, we have calculated two criteria. One is total average waiting time, and the next one is total turnaround time. As in the last class only I explained, out of the different CPU criteria, CPU scheduling criteria, CPU utilization should be maximum and your throughput should be maximum. Whereas waiting time, turnaround time, response time, all these things should be minimum. Let us see some of the advantages and disadvantages of FCFS policy. One, the advantages are it's very easy to implement. Programming is very simple and no costly hardware is required to implement FCFS policy. The disadvantages are it is not suitable for time sharing system. Why it is not suitable for time sharing system is because it is a non-preemptive scheduling policy. In a non-preemptive scheduling policy, once any process gets the CPU, it will not release the CPU to the next process until it is completely executed. That's the reason it's not suitable for time sharing system. In a time sharing system, everybody has to get the CPU for some duration. Okay, and the waiting time is also not uniform. That we have observed from this example. For waiting time for P1 is 0. P1 will get the CPU immediately. For P2, it has to wait till the completion of P1. So for P2 it is 12. For P3 it is 32. For P4 it is 42. So in the case of first come first serve policy, the waiting time depends on who has entered the queue first. The process which entered the queue first, no waiting time. The process which is at the end of the queue, the waiting time is too much. So waiting time is not uniform. And the last drawback is CPU utilization as well as input output device utilization is also not so efficient in case of FCFS policy. Because if the first process is a very big process, means that will utilize the CPU for longer duration. So there the CPU utilization is more. Whereas the next process, if it's a very short process, means it will not utilize the CPU for longer duration, means its CPU utilization is less. So the bigger process, the utilization is more, or shorter process, the utilization is less. At the same time, if one process has not requested any IO operation, means it is not utilizing IO device. So its IO device utilization is poor. Some process need more IO operation, means its IO device utilization is more. So uh, CPU utilization is also not perfect and not efficient, and IO device utilization is also not efficient. Let us take the second policy called SJF, also known as shortest job first. Here, as the name indicates, whenever the CPU is available or whenever the CPU is free, in the case of FCFS, it is allocated to the process which has entered the ready queue first. Here, it's not like that. Here, whenever the CPU is free, it is allocated first to the process which has short CPU burst time. The process which need less CPU burst time gets the CPU first. The process which need more CPU burst time or which has more CPU burst time will get the CPU last. So higher the CPU burst time, less priority is given for that process while allocating the CPU. And shorter the job and the more priority, higher the priority, that job will get the CPU. So if two processes have the same CPU burst time, in that case, who will get the CPU first? That is decided again by FCFS algorithm only. So in the case of SJF, whenever two processes have the same CPU burst time, in that case, we apply FCFS algorithm to break the tie. So the out of the two processes with the same CPU burst time, one which has entered the ready queue first will get the CPU first. And just similar to FCFA, a SJF algorithm also a non-preemptive nature. Here also, first the CPU is given to the smallest process. That will after only that process execution is over, it will the CPU is given to the next shortest process, next shorter process, next shorter process. Finally, the CPU goes to the process which is need the CPU, which has a more CPU burst time. But here also, once the particular process gets the CPU, mean it will the CPU is allocated to the next process only after the previous process execution is completed. We will consider the same example, and again here also we will calculate both average waiting time and CPU burst, total turnaround time. Here also same process I have considered P1, P2, P3, P4, the same time requirement 12, 20, 10 and 8 milliseconds. The case of shortest job for who will get the CPU? The process with a short CPU burst time. Out of these four processes, P1 has the shortest burst time of only 8 milliseconds. Means first the CPU is allocated to P4 first. So first P4 will get the CPU. That will utilize the CPU for next 8 milliseconds. Then after P4 is over, the next shorter one is P3, that is 10 milliseconds. Next, from 8 to another 8, 10 milliseconds, P3 will get the CPU. Next, after that, next shorter one is P1, that will utilize the CPU for next 12 milliseconds. So 18 to 30. And last, since P2 is the biggest job or the largest size job, that will get the CPU at the last mean from 30 to another 20 seconds. That process will hold the CPU. In the case of FCFS, the CPU is given first for P1, then for P2, then for P3, then for P4. No need to check any CPU burst time. In the order only you have to give it. Whereas in the case of shortest job for first the shortest one, that is for P4, followed by P3, followed by P1, and finally P2 will get the CPU. Here also we calculate both the waiting time and the turnaround time. So here in the case of shortest job for first we will take the process called P1. Its waiting time is 18 because it has to wait till the completion of both P4 and P3. P4 need 8 milliseconds and P3 need 10 milliseconds. These two summation is 18 milliseconds. So for P1 it is 18, for P2 it is 30, for P3 it is 8, and for P4 it is 0. P4 it is. Just add them, divide by the number of process 4, you will get 14 milliseconds. How much you have got it in first come first serve? It was 21.5 millisecond. Average waiting time is 21.5 millisecond. Whereas in the case of shortest job fast, it has reduced to only 14 milliseconds. So we know that while selecting a CPU scheduling algorithm, the one which has lower average waiting time is considered as a better algorithm. So out of first come first serve and SJF gives lower CPU, lower average waiting time. On the same basis, you calculate the turnaround time also for all the four process. Turnaround time is time of submission to time of completion. At what time the particular job is execution is completed, that time you consider. So for P4, it is 8. For P3, it is 18. For P1, it is 30. And for P2, it is 50. Add them, you get 106 milliseconds. In the previous case, it was in the first come, first serve. Even the average the turnaround time is also 136. Here it has reduced to 106 milliseconds. So both average waiting time as well as total turnaround time, we got lower value in case of SJF when compared to first come, first serve. But this may not be true always. Let us see the advantages and disadvantages of SJF. Similar to FCFS, it is also very easy to implement. And the waiting time is generally lower than FCFS. And the throughput is more. What do you mean by throughput? How many jobs we can complete it in given time, we call it as a throughput. So here in the case of SJF, what happens here? Initially, shorter jobs are executed first. Mean in a given, suppose some 20 milliseconds of time is given to you. Mean if the first three jobs have the time only 5 mean, then all the four jobs you can complete it. So totally, how many jobs we can complete it? We call it as a throughput. So generally, throughput is more in case of SJF when compared to FCF. In case of FCF, what happens is the first job itself is a bigger job. Mean it will the CPU cannot be allocated to the next job until the completion of the first job. Mean generally throughput is lower in case of FCFS when compared to SJF. But SJF suffers from three major drawbacks. It is also non-preemptive in nature. No need to explain again what is non-preemptive. And here what happens is lengthy process have to wait for more time because short process will get the CPU first. The other one is each time during allocation of the process, the entire ready queue has to be searched to identify which is the process which has the lowest CPU burst time. Allocate the CPU to that one. After the execution of one process over, again search the entire list to pick up the next process with the next CPU burst time, lowest CPU burst time. So each time we have to search the entire ready queue to identify the process with the lower CPU burst time. So that takes little bit extra time. So today I have explained two different CPU scheduling, two CPU scheduling policies of the same nature called non-preemptive. Okay. And we also learned how to calculate the average waiting time, how to calculate the turnaround time in both the cases. We also discussed about the merits and demerits of these two. So in the examination, one question definitely from a CPU scheduling policy, it could be like this. Explain FCFS and SJF algorithm in detail. Here you have to give their feature, their advantages, disadvantages. You have to consider a simple example also. Find the average waiting time and the turnaround time for the following processes in FCFS and SJF. Already I have given one, I have illustrated with one example. You try to solve this one as a second example. So let us take some simple 5 multiple choice questions on today's class. In shortest job first, more the CPU burst time. In the case of shortest job, more the CPU, the priority is less actually. So less is a priority, more is a priority. Priority does not change. None of the correct answer is A. Main drawback of FCFS, high average waiting time, high throughput, high turnaround time, both A and C. Because throughput will not be high in case of FCFS. So A and C are both are high. So the correct answer is D. So the correct answer is not D. It is D, not C. Make the changes there. It is D. Time required by the process for execution is called as burst time, turnaround time, response time, and waiting time. It is CPU burst time. The correct answer is A. Which of the following is not suitable for time sharing system? SJF, FCFS, both A and B, only B. The correct answer is C, because both SJF and FCFS comes under the category of non-preemptive. Non-preemptive algorithms are not suitable for time sharing system. And the last question is, if the CPU burst time is lower, then dash will increase. Throughput, priority, speed, none of this. The correct answer is throughput. But only in the case of SJF, the CPU burst time is lower, then the priority is more, but not always. Generally, CPU burst time is lower means throughput will increase in all the algorithms. So with this one, I'm going to conclude today's class. In the next class, we'll discuss about some more CPU scheduling policies. Thank you.